Hey everybody. In this video we're going to be talking about three different variables and as they pertain to gases. So pressure, volume, and temperature. The first one we're going to start with is pressure because this is one we haven't really talked much about up until this point. Pressure in terms of a gas is measured as the amount of collisions between particles. So if there are more particles colliding, that is going to result in a larger pressure. So as you can imagine, as we are all on Earth, there is an atmosphere of gas constantly surrounding us. If you want to remind yourself, could just give yourself a little fan really quick. That's air, that's gas molecules. And so as those gas molecules are colliding with your face and other surfaces, they are exerting a pressure. At sea level, we are experiencing 1 atmosphere of pressure. So that's 1 atm. And it's something that we're used to. We've been experiencing it our entire lives. But there's a way to experience the true force of pressure. And I have my handy assistant here, Mr. Miller, who's going to help demonstrate this. So you can do this one at home too if you would like to at any point. All you need is a gigantic garbage bag, a vacuum, and a willing participant, or a moderately willing participant. All right. So squat in the bag, please. Thank you. So right now, sorry, I'm going to do an explanation. So right now there is gas on the outside of the bag and there's gas on the inside of the bag. So right now there's a pressure equilibrium. So the collisions that are happening on the outside of the bag are equal to the collisions that are happening on the inside of the bag. So now what I'm about to do is I'm going to put a vacuum in the bag and I'm going to suck all the air that's inside of the bag. So then there's going to be no collisions happening on the inside of the bag, but there's still going to be collisions happening on the outside of the bag. So since there's a barrier between Mr. Miller's body and the air, there will be nothing to create a pressure equilibrium. So you're going to experience pressure for the very first time. Are you ready?
I'm ready.
Okay. Are you under pressure right now?
Squat pressure.
All right. So hold that, please. You have to make sure that the vacuum does not catch like your clothes or like the bag or anything like that. So it usually helps if you like hold it in between your legs, so then it's not like around anything. All right, you ready?
Mm-hmm.
There we go. 1, 2, 3. Oh, I caught something. All right, what does that feel like?
Lots of pressure.
Can you stand up?
Nope.
Try.
Try it.
Try. Try standing up.
I'm trying to think.
Uh-oh. No, she's upset. Okay. Whew. What did that feel like?
Felt like a very, very strong hug over my entire body.
Like how strong?
So strong that I couldn't stand up.
Okay. Cool. So you can try that if you need like some quarantine entertainment for yourself right now. Thanks. So basically, again, what was happening there is because of the collisions that were happening on the outside of the bag and no collisions happening on the inside of the bag, it created, it disrupted a pressure equilibrium, which is why Mr. Miller was experiencing that. I'm trying to get my iPad screen back up. Cool. So that is pressure. So again, the main thing that you need to know here is that pressure is measured as the amount of collisions between particles. The more collisions, the more pressure. Since pressure is something we haven't talked about a ton, I want to quick review the common units for pressure that you could be experiencing in this unit. So one that I just previously mentioned was atmospheres. That is abbreviated to ATM. It's based on the idea that on Earth we have 1 atmosphere above us. So at sea level, you are experiencing 1 atmosphere of pressure. If you go up in the atmospheres, like on the top of like Mount Everest, you would have less atmospheres of pressure. And if you were down in Death Valley, you would have more atmospheres of pressure. Some other common units of pressure are millimeters of mercury, torr, pascals, and kilopascals. And really all of these are kind of used with similar frequencies. There's not like one that's used more often than the other, so I do want to make sure that you're comfortable with all of these. Millimeters of mercury is literally based off of the name that you see. What they did is they created something called a manometer, which is something that can measure pressure. And what they did was they had a tube, like a test tube, that was a complete vacuum. And then they filled it with liquid mercury, because as you know, mercury is a liquid at room temperature. And then atmospheric pressure pushed down on the mercury and then caused the test tube to then fill up with that liquid mercury. And the liquid mercury filled the test tube up to 760 millimeters. So that's where that came from. Millimeters of mercury and torr are actually the same quantity, they just have different names. So 1 atmosphere is equal to 760 millimeters of mercury in torr. I don't have an interesting story for pascals, it's just another unit. And kilopascals, 1,000 pascals is in 1 kilopascal, just like 1,000 meters in a kilometer. So there's 101,325 pascals in an atmosphere and 101.3 kilopascals in an atmosphere. So these are some common units that you might see. Another unit that I want to talk about in terms of gas laws is temperature. So as we know, temperature is a measurement of the amount of kinetic energy that particles have. The word kinetic means movement. So this is basically movement energy. So how fast particles are moving. So if particles are moving faster, they have a higher kinetic energy, therefore a higher temperature, and vice versa. One key thing that you need to know about temperature in terms of gas laws is the unit that we measure it in. We always measure temperature with gas laws in Kelvin, if you haven't heard of that before. Kelvin is another temperature scale, just like degrees Celsius or degrees Fahrenheit. The reason that we use Kelvin with gases is because the Kelvin scale actually doesn't have any negative numbers. As you know, degrees Celsius is based off of water. So water freezes at 0 and boils at 100, and that was kind of like the parameters that were set, but that lends itself to negative numbers. Same thing with the degrees Fahrenheit. The problem is when you have a negative temperature, math, you might end up with a negative something else. So we needed a temperature scale that didn't have negative numbers for the purpose of calculations. The reason that Kelvin doesn't have any negative numbers is because Kelvin is based on this idea of absolute zero. Absolute zero is 0 Kelvin. And 0 Kelvin, if temperature is kinetic energy, is movement energy, 0 Kelvin is the theoretical temperature at which molecules stop moving. Because if molecules stopped moving, they would have no kinetic energy and therefore no temperature. And that is considered to be 0. I say theoretical temperature because as far as we know, we haven't reached it yet. It hasn't occurred naturally in nature, and even in a laboratory setting, they haven't quite gotten to it yet. So we haven't been able to cool molecules enough to have them not move whatsoever. But that's kind of what this is based off of. It's very cold, just to be clear. 0 Kelvin is the same thing as negative 273.15 degrees Celsius. Just to give you an idea, that's about negative 450 degrees Fahrenheit. So that's very, very, very cold. So here's the problem that we run into as scientists, is usually most thermometers that we have measures in degrees Celsius, and not a lot of thermometers measure in Kelvin. So if we take a measurement in Celsius, we need to be able to convert it to Kelvin. Lucky for us, it's kind of easy. You just add 273. So for example, room temperature is generally described at being 25 degrees Celsius. So if I was curious what that temperature was in Kelvin, all I would do is I would add 273 to that. So room temperature would be 298 Kelvin. So you can take any degree Celsius number you have and add 273 to get to Kelvin. But the thing is, you have to do this with all gas laws, always and forever. The other variable that we're going to be using fairly often is going to be volume. I don't have a lot of special things to say about that because we've been working with volume quite a bit up until this point. Volume is simply measured as the amount of space that particles take up. So, for example, if I'm talking about a balloon, this balloon has a smaller volume than this balloon, because it's simply how much space the balloon is taking up. So the amount of space gas particles are taking up is the volume. So with that in mind, we're going to play around with some relationships here. And if you remember that simulation I had you guys do earlier, having a really good model of how gas particles behave helps with this a ton. So looking at this, if temperature goes up, okay, temperature goes up, that means particles are moving faster, right, because that's kinetic energy, always measured in Kelvin. Do you think pressure would go up or down? Remember, pressure is measured as the amount of collisions. So if particles are moving faster, do you think they'd collide more or less? The answer is more, which means if temperature goes down and if particles are moving slower, collisions would happen less often. What about the volume of the container? So what if you had a larger container? So you've got a sample of gas and then you put it in this really big container. Do you think particles would collide less or more? The answer is less. Same thing, if you had a very, very, very small container, the particles would collide more. What about the number of molecules? What if you just pump some more molecules into a space? Do you think they'd collide more or less? More. If there's less molecules, they would collide less. So this is something we're going to be playing around with a lot this unit, conceptually, numerically, different things like this. This is something that you should feel comfortable with imagining these particles in your head. So one thing I want you to note here is that pressure was always the dependent variable. Basically meaning if you want to change the pressure of something, you need to influence another variable first. You cannot directly impact pressure. You can only you can only affect pressure by affecting other variables that are within your control. So on this idea, pressure is then directly related to temperature and the number of molecules, and then it is indirectly, it's indirectly related to volume. And this is something that some later videos is going to talk more in depth with as far as the numbers go, but that's kind of what these relationships were here. All right, this is kind of your quick synopsis on pressure, temperature, and volume and how they will pertain to gases.